A very good afternoon to all of you. Remember, we are talking about the pitch, and in the last class, we spoke some of the observations about the pitch. Pitch, as we have all understood, is our own response to a given frequency of sound. Good afternoon, Rishita. In today's class, we are going to take that discussion forward. After speaking about the virtual pitch, in this class, we will talk about repetition pitch. Then we will take the discussion forward to something called as timbre or quality of sound. And then finally to Fourier analysis of complex tone. Good afternoon, Simran. Good afternoon, Nimishka. Thank you for saying that yes to my question. So, what is repetition pitch? So, this is a very common observation. In fact, if you have been a good observer, you must have noticed repetition pitch many a times. One of the places where you can feel repetition pitch is if you are, say, in a vehicle, bus or a car with windows open, sliding glasses open, and the the car is going on the road next to the divider at the center. So at some places the dividers has got bars. The central road divider has vertical bars. One of the example is the Marine Drive. If you go, there are central bars kept there which has regular intervals. The other examples, uh, in Mumbai, you will get it at JJ flyover, where the side barrier, not the central bar barrier, but the side barrier has repeated perforations. So what happens is the noise from the vehicle goes and hits those barriers which are placed at regular interval, and the reflected sound is has a kind of musical note to it because of the periodicity of the barrier. So if you are a careful observer, you can observe this easily. You can try to, if you have not yet observed, next time when you are in such situations, you can observe it. There are various other ways by which this can be observed. The first recorded instance was from Christian Huygens, the the one guy who is responsible for the wave theory of light. He actually heard the sound from a waterfall or fountain, not waterfall, fountain, hitting the staircase and getting reflected back. So, what happens is typically a fountain, a waterfall, or maybe a blowing wind in general, they are broad spectrum noise. They have various frequencies from very low to very high value. So, a broad spectrum noise hits a physical feature which has repetitions. You can see that it has multiple repetitions. So sound goes and hits here and come back. But the sound which goes and hits the next repetition and hits come back will have some time delay. And this time delay is periodic, you can see. So what this person would be receiving is sound at some periodic delay, and therefore if had this been not there, you would hear only noise. But if this is also there, then you will hear some sort of pitch, some sort of frequency which is superimposed on the noise. So on one side noise is still available, but this also comes into it. This is typically what is referred as repetition pitch or repetition pitch. whichever way you pronounce it. So this is the idea of it, and there are various other ways by which you can observe. People have observed it and recorded it. The other example is the example by Mignard, who in 1941 reported this. So this is the steam engine. He's standing on a platform. The sound comes directly to him, and sound comes reflected from the platform surface to him. And now this reflected sound will interfere with the original sound, and that may create some sort of pitch like sensation, some frequency. So that is another example. The third example listed here is an experiment which was performed by Hermann 1912. This is an interference between, so what he is doing is there is a tap water. Again, as I said, tap water is a kind of a mini waterfall. The tap water generates sound which has huge broad range of frequencies. All those range of frequencies are fed here. Now what he is doing is he is filtering out the frequencies by using a tube length, a variable tube length, and trying to hear it out. So what he is doing is he's listening on one hand the direct sound as the bass, and by changing this length he can sample out a particular frequency. This is another example of repetition pitch, interference between the noise of the running water and its reflection in a tube of adjustable length. So these are the examples of repetition pitch or pitches, whatever way you call it. In general, if you want to do an experiment, and this is a very much an experiment which you can try at home, at least the first case. So you can have a noise generator, broadband noise generator. This is one technical place which is fed to two speakers. So one is the left speaker, one is the right speaker, and the obviously the noise is same in both, but the person is not sitting at the center. Person is sitting at some distance away from the center. So if one side is distance a, the other side is distance l more, so a plus l, so there is a dissimilarity, a time delay between these two. So this sound will reach person quickly, this sound will take longer, so there will be a time delay from this, and this time delay actually forms the sensation of the pitch. How much delay will happen? So very straightforward. If v is the sound speed, then the delay will be L by V, where L is the extra distance which is there between the observer and this source. So T is equal to L by V, where V is the speed of sound. What the pitch the person will perceive? The pitch perceived is 1 over T or V by L. So this is another example where the pitch can be perceived. So as I said, these are doable experiments at home. Noise sources are available these days on various online, various noise tracks are available any which way. So you can just Google a broadband noise and you will get a lot of noise tracks available. Remember, acoustics experiments, almost most of the recording is available on internet. You can download and perform various kind of experiments. So right now, focusing on this, you can download a broadband noise track, play it through the speakers, keep them at two different distances, and try to sense. You can also perform the Huygens first experiment. If you have a Bluetooth speaker or anything, then you can take it to the staircase of your home or some nearby building, where ideally you should get a little bit an open staircase. If not, even if it is closed, you can try and see if you can get some result. So you can perform these experiments. Typically in this case, you will get a time delay of 1 to 7 milliseconds, and that can give you a variable frequencies or variable pitch frequency depending on how far you are from one or other sources. So all these things can be calculated. Now that leads to the another phenomena to for us. Pitch, remember we were talking about since last class. The pitch of a sound basically is our response to a given frequency. Source may produce pure frequencies, but our response is not so pure. It's complicated as we have seen. We can perceive pitch even if the fundamental is absent. We can perceive pitch even if there is no pitch, just like in repetition pitch. And otherwise also the pitch response can vary depending upon its loudness, how short it is or how long it is. We have seen in the last class that if it's very short, the pitch cannot be sensed. It appears like a click. Unless and until it increases in length, we don't get the idea. But beyond pitch also, there is something which we have to understand. And that something is called timbre or quality of sound. It's a very subjective notion, though there is no scale for it to measure, but still it is very much real. It is that attribute of auditory sensation in terms of which a listener can judge two sounds similarly presented and having the same loudness and pitch as dissimilar. That means they have the same loudness and same pitch, but it is dissimilar. So loudness and pitch, same kind of loudness is there, same kind of frequency is there, but it is dissimilar, it is different. So let me give you an example. Yeah, sorry. Let me figure out. So I'll give you one example of a sound here. Let me see if it works. Okay, so I repeat this once again. You could hear that the sounds were different. But to tell you the fact that it has the same loudness and it has the same pitch. Both are same. Loudness is same, pitch is same, but you can see that the sounds are dissimilar. I repeat once again. So you could make out that there are differences. So that difference is typically referred as timbre or quality. Okay, so let's try to focus on what makes a similarly presented sound, same loudness and pitch, but make it appears to sound different. That is what we call timbre and quality. As I said, it's a very subjective notion. It is impossible to construct a scale for it or measure it in a numerical manner. So generally what we do is we use verbal attributes. Now what is a verbal attribute? Something like this. The sound, depending on how it is felt, it can be pure, it can be rich, it can be cold, it can be warm, it can be dull, it can be brilliant. Or it there is some more scale like full or empty, compact, scattered, colorful, colorless. Now, having said this, there are no uniformity, there are no uniform standards, there are no common standards for timbre measurement or timbre discussion. Helmholtz has number of observations. Some of the observations are worth sharing and talking. As your sound studies goes deeper, these observations will come handy. In fact, these observations are very important when somebody is designing a musical system, somebody is buying a musical system, somebody is designing an acoustic theater for acoustical performances, etc. These observations are very handy. What are these observations? Very simple. Simple tones have very soft, pleasant sound, free from roughness, but dull at low frequencies. So if you have a pure tone, simple tone, like a tuning fork, pure organ pipes, then they have a soft, pleasant sound. Roughness is not there, but it's dull at low frequency. You can see that all these attributes are normally, they are not numerical attributes. We cannot assign some numerical attribute. It is by careful observation and the kind of response people give to the sound, from that we can decipher. Musical tones with moderately loud series of harmonics up to sixth sound. Up to sixth sound, it's rich. It's richer. It feels richer. If you have up to sixth sound, means if the harmonics are present and up to sixth harmonics, it sounds fairly rich and more musical than simple tones. So it will sound, if more harmonics are playing, it will, you feel that it's more musical, it's richer. Some of the orchestra music is that way. And it also remains sweet and soft up to sixth sound. But then there are more harmonic, then there are issues. Examples are piano or the French horn. Tones consisting of only odd harmonics. So if there are only odd harmonics, even harmonics are missing, then it sounds hollow. And if many harmonics are present, so only odd harmonics, but if there are many large, more than six, then it also sounds nasal. So there are many musical instruments that sounds nasal. There are many what you call many singers who sounds nasal, and you know whom am I talking about, your favorite singer from Bollywood. So yeah, so when the fundamentals are predominates, when the strong fundamental sound is there, and we are going to talk in detail, the quality of tone is rich, and when the fundamental is not sufficiently strong, the quality of tone is very poor. So these are the observations. One, when one designs the music systems, one when you purchase the speakers, all these factors come into play. So one has to be very, very careful. Complex tones with strong harmonics above or sixth or seventh are very distinct, but the quality of tone is rough and it's cutting. So I can go back and see that note which I had presented to you. In this note, what is happening is, now let me explain. In this note, what is happening is the first tone is a pure tone. As you go to the next tones, the number of harmonics are constantly increasing. As the more number of harmonics comes, initially it sounds much slightly more richer, but towards the end the sound appears to be rough. So please observe it, listen to it once again very carefully. So you could see that how the sound becomes crappy or rough as you extend the number of harmonics in the sound. That brings us to the Fourier analysis. Remember, the Fourier analysis remains one of the most important tools available to us to analyze the sound. So, since we are talking about the fundamental and harmonics, we are talking about the Fourier analysis. So, Fourier analysis, I have two examples of tones here. Both of these has first harmonic and second harmonic. But what is happening is here the first harmonic and second harmonic are equally loud. They have the same amplitude. Here first harmonic is loud, strong fundamental but weak second harmonic. These two sounds resulting waveform looks different. You can see this one is this way and this one is this way. And what is happening here is these two sounds will sound different. You can see that the pitch is the same in a sense that the time period of this or time period of this complex waveform and time period of this complex waveform, it's identical. So basic frequency is the same. So pitch will be the same, but still the sound, they will sound differently. Their timbre is different or the quality is different. Then this is another example whereby I have second harmonics which has the same amplitude as the first one. But now the second harmonic is phase delayed. You will see that this harmonic starts with the phase pi, this phase 0, then this harmonic starts with the phase pi. So it goes towards positive and this goes towards negative. Now if you add the two, again the fundamental pitch remains the same, the time period or the frequency remains the same. But you would find that the resulting sound has a very different quality than in this and this. That is what differ them in what is called in their timbre. So that brings us a more detailed discussion on Fourier analysis of complex tones. Remember, most of the time, I mean, my last slide made it clear that what is timbre and sorry, what is timbre and how does it affect the quality of the sound. Even if the sound loudness is same, you can see that this amplitude is roughly same as this amplitude. This pitch is same, pitches are identical, this has the same pitch as this, but still when you hear the two sounds they will sound differently. So that is what it is all about. Now, since we're talking about the Fourier analysis, let's do a little bit of groundwork because now Fourier analysis will also guide us a lot in acoustics. If you have a pure tone, then it has only one frequency, whichever frequency. Its Fourier spectrum looks like this. It has only one waveform. I have not shown it. Depending on whatever its amplitude, a graph of amplitude versus frequency can be plotted. This kind of graph is normally referred as Fourier spectrum. You have done this in your mathematical physics course, Fourier analysis. You know that if you have complex waveforms, they can be broken down into simpler waveforms with different amplitudes. Now, if you plot the graphs of those amplitude versus frequency, then it is called Fourier spectrum. Now here are two examples. One example is a sine wave of frequency f1 having an amplitude 1. This is what it means. While here it means that the frequency, a sine wave of frequency 3 times f1 having an amplitude zero point 0.5 is presented. So this is a pure tones Fourier spectrum. This is how it looks like. Now you can go ahead and discuss all type of things. So first type that we are going to relook again is a square wave. You have done this derivation, Fourier components of a square wave. You have done this derivation in the lower classes, I mean earlier semesters. If this is your square wave, then a square wave has a dominant fundamental of the same frequency as that of the square wave. So whatever is the time period, that is the time period of the fundamental. And then it has odd harmonics present. So n is equal to 3, 5, 7, 9, odd harmonics present with successively decreasing amplitudes. How does the amplitude decrease? So if this has fundamental has an amplitude of 1, then each harmonic which is present will have an amplitude which is the amplitude of the fundamental divided by number of harmonic. So third harmonic will have an amplitude 1 by 3, fifth harmonic will have the amplitude 1 by 5, seventh will have 1 by 7, so on and so forth. So the amplitude decreases. Okay. Now when you add up all these things, you will get these kinds. So if you add the first two, you will get this waveform. If you add the first three, you get this. If you add all these 5 waveforms, you get this. So as you add up more and more waves, you will reach more and more perfectly to a square wave. How would its Fourier spectrum look like? It is going to look like this way. So on the y-axis you plot amplitude, on x-axis you plot frequency. If your fundamental is f1, then we assume that its amplitude is 1. So this is drawn as a short line, thin line, very thin line. Although here it is shown as little broader, but it's very thin practically. Then what theoretically this width is 0. Practically in real system this width will not be 0 in real observations. Here again, then this is the next harmonic, n is equal to 3. Remember its amplitude is 1 by 3. Frequency is 3 times fundamental. So if this is f1, this is 2f1 which is missing. This is 3f1 and it has amplitude which is 1/3 of the first one. Then you have the amplitude 1/5 for 5. So at 5 times f1, you have still smaller amplitude, still smaller and still smaller. So this is how the frequency spectrum of a complex tone like square wave would look like. These are higher frequencies. This is fundamental. These will be called as lower frequencies. This is how a triangular wave look like. This is a triangle. A triangular wave only has again odd harmonics, but it has amplitudes falling uh, proportional to the inversely proportional to the square of the harmonic. So for third harmonic it is 1 by 9. For fifth harmonic it is 1 by 2/5. So on and so forth. It drops very quickly. A sawtooth waveform has all the harmonics present and the amplitudes don't drop so quickly. It drops slowly. So this is all the harmonics being present. So this is another very important analysis, that mathematical derivation you have done for all of these earlier. This is one of the most important. This is for a short noise. If it's a short noise, then it has a one single spike. Okay, this is not to the scale. This graph is amplitude versus time. On the on the x-axis it's time. On the y-axis it's a amplitude of sound. It's a shot like a gun fired. It will produce a very narrow spike in the sound intensity, and that's it. Now, what would be the Fourier analysis of this look like? So, Fourier analysis of this would be adding lot of sine waves with same amplitude, all the harmonic. Just keep adding, 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 adding. When you do that, you would find that at one point the amplitude starts rising because this, 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 at this point they are always in phase. So this amplitude will keep rising. At other points, sometimes it's phase in phase for some combination. For some combination, it will be out of phase. So it will keep adding, cancelling, eventually adding. So at all places, it will amplitude will drop, and at center point, the amplitude will rise. As you add more and more terms, this will lead to a spike here at the center, suppression at the ends. So this is another example, and it's very important for Fourier analysis of short noise. Anytime if there is a very pulse of sound, small pulse, then Fourier analysis, Fourier's graph will look like this. Fourier spectrum, it has all the amplitudes with all the frequencies present, having amplitude as 1, which is same as the amplitude of the short noise. So this is how the Fourier analysis of a complex tone look like. I am summarizing all these results in a very single slide in this case. And I would strongly recommend that you by heart this slide. This is very, very important for the exam. By the way, this slide I have not taken from our primary reference, but I've taken it from our secondary reference, that is Berg. Berg's book is available again mostly on for downloading, and Indian edition is also available. So you can figure it out and how to access it. But whatever is relevant needed, I have put it over here. Remember, for the exam, we will generally don't go beyond our lecture content. So stay focused on that. Almost all the lecture content is available. Videos are available. So stay focused on that. So again, I'm summarizing. These are the harmonics 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are the different types of waveforms. We have done pure tone, sine, triangle, square, sawtooth, also called as ramp, and the pulse train, bullet fired at regular interval. Then this is the fundamental. Here in a pure tone only fundamental is there, rest of the harmonics are missing. In triangle and square only odd harmonics are present, even harmonics are missing, so their amplitude is 0. Although remember, in triangle amplitude drops much faster compared to the inverse square of the number of harmonics, while in square amplitude decreases slower, just proportional to 1 over number of harmonics. In sawtooth, again all the harmonics are there, but their amplitude drops slowly. In pulse, all the harmonics are there, but the amplitude doesn't drop. It remains same for all the number of harmonics. So this is how it would look like. I strongly recommend you people to memorize this table. You have done a lot of Fourier analysis in your previous semester. In this semester, you don't have to do the mathematics of those discussion, but a summary and overall understanding of the phenomena is very much needed, because that affects the quality of sound here. So with this, I think we can stop in this lecture. Thank you.